We're going to start off with marginal probability, which is the probability of a single event without the consideration of another event. Control is, there we go, of a single event without the consideration of another event. Okay, and we're going to call that probability of A. Okay, so say I was going to do this, but then I forgot to grab the index cards on my way out. But let's say I hand you guys all index cards, and I give the boys blue index cards, and I give the girls pink index cards, and I ask you to write on that index card whether or not you like statistics. So it's just yes or no. Okay, so there's, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14. All right, so there's 14 cards. I take them all, I put them in an envelope, I pull one out. So what's the probability that the person says yes? Okay, a single event without considering anything else. Okay, so just a one single pull out of everything. Okay, so everything I'm looking at. Whereas conditional probability is the probability of an event given another event has already occurred. Okay, so the probability an event will occur given another event has already occurred. And then we're going to call this probability of A given B. So it's going to look like this. A with like a straight line given B. Okay, so I put the card I pulled back in the envelope, and now I pull out another one. And I observe the card, and I see that it's blue. Okay, so given that I've pulled a blue card, so given that the person is boy, what's the probability that they said yes, they like statistics? So given that there's some other condition, and it'll say it in the problem when we look at some examples. So given there's some other condition, what's the probability of that event occurring? So I've only got 5 boys in here. So there were only 5 cards that I could have drawn that were blue. So that probability would be whatever the yeses were out of 5, as opposed to in the marginal probability, that was out of the whole class, so that was out of 14. So the denominator is going to be different in that. So the denominator is that given. So if it says given this event occurred, that becomes your denominator in the probability, and then A is your numerator. Okay, whereas in this one, A is your numerator, but your denominator is just the entire sample. And we're going to do some examples. Let's do some more definitions here. You have mutually exclusive events are events that cannot occur together. So it gets kind of confusing when you're asking the mutually exclusive. It's almost kind of opposite, because if they are mutually exclusive, then they cannot occur together. Like, can you win and lose a game at the same time? Okay, no, you can't. Since you cannot, they cannot occur together, then winning and losing is mutually exclusive. Okay, or can you get heads and tails at the same time on a single flip of a coin? No, you cannot. So they are mutually exclusive. So if the answer is, can they occur So the question you ask, can the event occur at the same time? The answer is yes. Okay, then, you ask the question, can the event occur at the same time? And the answer is no, then yes, they are mutually exclusive. Okay, can they occur at the same time? Yes. Okay, then they're not mutually exclusive. So it goes opposite. So an example of not mutually exclusive would be you can be a boy and not like statistics. Those two things can happen at the same time. Okay, or you can like vanilla ice cream and strawberry ice cream. Okay, you can like two different things. Independent events are events that do not affect each other. Okay, and I'm going to put underneath here with a star, the denominator is the same every time. So an example of an independent event would be a coin toss. Okay, every single time you toss a coin, you have a 1 out of 2 chance of getting heads. A 1 out of 2 chance of getting tails. And then dependent events are events that affect each other. Where the probability changes every time. If I could spell, that would be helpful. Probability changes. The denominator will change. Okay, so an example of this is I open a bag of M&Ms. Okay, there's 30 M&Ms in there, and 8 of them are blue. Okay, the probability I pull a blue M&M, 8 out of 30. Okay, I pull a blue M&M and I eat it. How many M&Ms are left in the bag? 29. How many blue M&Ms are left? 7. So what's the probability that on the second pull, I pull a blue M&M? 7 out of 29 now, because there's only 29 M&Ms left, and I ate one of them. One of them's blue. So the denominator changed because you changed something in that first trial. You already pulled one possibility out. Okay, whereas this one, M&Ms wouldn't work independent because it would be dependent, but the coin toss, every single time it's the same probability. Okay, the coin basically resets itself. Or if I were doing the M&M, if I wanted to make M&Ms independent, I would have to take the M&M out, not eat it, put it back in the bag, shake the bag, and then pull again. Okay, that's the only way they would be independent. All right, so let's do some examples here. So this is an experiment outcome. So let's say we have a slip of paper. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on them. On each paper is numbered. And I'm going to do 3 separate pulls out of the piece of paper. Okay, and then these are the outcomes. So the way this is given to you is the first pull for each set of experiments. I got a 2, a 1, and then a 2. And the second pull, and then the third pull is kind of the way it's given. So let's look at this. So which events are mutually exclusive? So what you're doing is this. Can these happen at the same time? So if I'm doing on my first pull a 2 and a 1, so let's look at A and B first. I can't pull a 2 and a 1 at the same time. Okay, or sorry, my sample space. In each pull, I've got 2 different bags. Okay, so in this bag I pull a 2, this bag I pull a 1. All right. That's what we're looking at here. A 4 and a 9. Okay, no. And a 6 and a 10. No. So none of them are in common. So that's what we're asking. Do they have anything in common? So if no, they do not have anything in common, then yes, they are mutually exclusive. So we would say A and B are mutually exclusive. Okay, then we can look at A and C. So on the first poll, I get a 2 on both of them. Okay, now they have something in common, which means those are not mutually exclusive. Okay, they can occur at the same time because they both have the 2. Okay, so A and C are not mutually exclusive. Okay, then look at, you did A and B, A and C. Now you have to look at B and C. So do they have anything in common? No, so that would be B and C. I don't really like that example. Let's move down to a few other different examples, but this would be A and B or B and C. You're going to see a lot of these. Okay, these are called two-way tables. So the two-way tables, you've got 2 categories. So this is similar to the first example I posed, where I separated the index cards blue and pink, and then I asked a yes or no question. So this is the same thing, okay? So this time we separated by boys and girls, and we asked the question, do you worry about having enough money? Yes or no. Okay, and these are how the results are summarized. This is called a two-way table. What you're going to want to do is complete the two-way table by adding, okay, down and across. So 4 plus 7 would give me 11. 10 plus 9 would give me 19. And then across, 4 plus 10 would give me 14. 7 plus 9 would give me 16. And then if you add the bottom column and the last column, you should get 30 both ways. So what that tells me is I surveyed a total of 30 people. Out of that 30 people, I had 14 boys and 16 girls. And then out of my total survey, I had 11 yeses and 19 no's. And then I broke them down boy and girl into the table. So now you want to look at your probability. So, okay, you've got the blue and the pink index cards in your envelope. And we're going to do find the probability that I pulled a card that said, yes, I worry about having enough money. Okay, so that is just a one-time thing. It's not given anything special. So find the probability of yes. So what we would do there, okay, yes. How many people said yes, they worry about having enough money? Total. Okay, I didn't hear, sorry. 11, yeah. So you had 11 people that said yes out of a total of 30 in my envelope. And then we would want to do, we can do 3 decimal places for these. So 0.367. Okay, I put that card back in the envelope and I shake it up. And I'm going to now find the probability that I pull a pink card. Probability of a girl. How many total girls? 16 out of a total of 30. So that would give me, let's see, 0.533. Okay, now these are both singular events. Okay, I didn't consider any other events. So these are both examples of marginal probability. Okay, now the next one, find the probability that the person does not worry given that the child is a girl. So here's what happened. I put these cards back in, shook the envelope again. I pulled out, okay, first start at the given. I pulled out a pink card. Okay, I didn't open the card yet to see if it was a yes or no, but I pulled out a pink card. So start with the given. That's your denominator. How many pink cards do I have total? 16. 16 girls total. So out of the 16 that are pink, what's my possibility that the person said they do not worry that were pink? What was that? I'm sorry. 9, yeah. 9 out of the pink ones said they do not worry. So 9 out of 16 there. And then 9 divided by 16, 0.563. Okay, so that's conditional probability. So these two are both conditional, where the given is your denominator. So find the probability is a girl given the child worries. So given that I pulled a card that said, yes, I worry, how many of those are pink? So my denominator is the yes worries. How many total yeses did I have? 11. So I'm looking here. And then probability is a girl. How many girls said yes? 7. So 7 out of 11. So 0.636. All right, are the events worried about money and not worried about money mutually exclusive? You got it? Okay, yeah, because we're looking at the given first. So the difference here is that I pulled a pink card. I looked at the part that it was pink first. So I said, out of the pinks, how many? And then this one was, I pulled a card that said yes, but I'm colorblind and I don't know what color it is. So then I looked to see what color it is. So when we say, are they mutually exclusive, can they happen at the same time? Can you be worried and not worried at the same time? Okay, in the survey, no, you had to say yes or no. So if the answer is no, they cannot happen at the same time, then the answer is yes, they are mutually exclusive. Okay, so you have to remember that little trick there. They're kind of opposite. Are worried and boys mutually exclusive? So can you be worried and be a boy at the same time? Yes. So if the answer is yes, then no, they are not mutually exclusive. Okay, independent are events that do not affect each other. So does being worried and being a girl, do those affect each other? Okay, well, if we look at the example here, okay, so the probability that you're worried would be 11 out of 30. The probability of girls would be 16 out of 30. Given the example, they don't really affect each other. Okay, given the example, no. But here's the fun thing about statistics. You could kind of argue this either way. Okay, sorry, given the example, yes, they are independent. No, they do not affect each other. Okay, because you could say generally that they could be dependent because girls tend to worry more than boys, right? You say girls tend to worry more than boys, and if someone says, well, that's a generalization, to worry. Okay, more, you could say, well, according to this survey, more girls said yes than boys. The probability of a girl saying yes was 7 out of 16, where boys was 4 out of 14. You can say the probability is there. The probability, what is that, 7 out of 16 as opposed to 4 out of 14. Okay, 44% to 29%. So more girls tend to worry more than boys. So you can argue that depending on what your survey results are. So is a survey of 30 good for something like this to generalize? No, you probably want to get 1,000 samples. Okay, then you can generalize things like that. But that's one of the things you want to look for when you're reading these so-called polls and statistics. How many people they actually ask? Okay, so that's one thing to look for. All right, looking at this example, so let's just say I just want to look here, boys and girls. So what's the probability that I pull a blue card, 14 out of 30, and a pink card, 16 out of 30? Okay, I add these two probabilities together, I get 1. Okay, so the sum of your probabilities, total probabilities, boy or girl, would be 1. So think about that when we go on to this next complementary event. So 2 events will be complementary if their probabilities add to 1. So a complementary event is going to be notated like this. So A with a line over it, P of A. Okay, you might have seen that with Venn diagrams, if you were doing Venn diagrams with an apostrophe instead of a line over it. So it actually means all of the outcomes that are not included in that probability. So the formula for P of A is 1 minus the probability of the event. So for example, okay, the probability that we pulled girl card was 0.53. Okay, what is the complement of that? So you would say P girl with a line over it. Basically, not girl. Well, that would be 1 minus 0.53, which would give us 0.47. Okay, let's look at an example with checking if events are complements of each other. So I toss a coin 2 times. So here's what can happen. Okay, you have 4 actual ways that you could get this. So you could get a heads on the first toss, and then get heads again. You could get heads on the first toss, and then tails on the second toss. You could get tails on the second toss, heads on the first toss, or sorry, tails on the first, heads on the second, or you get tails and tails. Okay, those are the only 4 ways that this could shake out. Okay, I'm tossing it twice. There's only 2 options each time. Okay, so you have events here. A, at least 1 heads is obtained. So let's do the probabilities first. So find the probability of A, that you get at least 1 head. How many times could I get at least 1 head in this option here? I could get it here, here, or here. So there's 3 ways that I could get at least 1 head out of 4, or 0.75. Probability of B, that you get 2 tails. Well, there's only 1 way that that can shake out. You get tails and then tails. So that last one there, so that's 1 out of 4. You get 0.25. If I add those 2 probabilities together, 0.75 plus 0.25, I get 1. So let's answer these questions. Are they mutually exclusive? Can I get at least 1 head and 2 tails at the same time? No, which means yes, they are mutually exclusive. So the answer, can it happen at the same time, is no. Then yes, they are mutually exclusive. Are they independent? Okay, so does one outcome affect the other? Yes, they do affect each other. So independent effect, they depend, yeah, no, sorry. They are dependent on each other, okay? So if I get at least one head, that I can't get B. Okay, so I can't get two tails. So no, they are not independent. They are dependent on each other. So you have to ask the question. The answer to the question is yes. Then the answer to dependent or independent is no. Same thing with mutually exclusive. They go back and forth. Are they complements of each other? Yes, because the sum of the probabilities is 1. All right, no dependent. All right, and with your outcomes here, you can also do something called a tree diagram. Is this in your guys's? Okay, cool. So it came out a little weird. Let me finish this off for you. I think you just had one other thing here. And okay, so this is basically how we can put all of the outcomes that we have. So you have a box contains a certain number of computer parts, few of which are defective. 2 parts are selected at random from this box and inspected to determine if they are good or defective. So G is when it's good, D is when it's defective. Okay, so you're pulling 2 parts out. So you're going to open the box, you're going to pull 1 part out. On the first part, okay, so that's right here. That's okay. On the first part, it's either good or it's defective. Okay, so that's this first tree branch here. Okay, then you do your second pull. So on your second pull, you can again have either good or defective. So if you pulled a good the first time, then on your second pull, you could have good or defective. So if you did a good part and then a good part, then your branch would be a good. If you pulled a good part and then on the second one a defective, it would be good, defective. If you pulled a defective part the first time, then a good part the second time, defective, good, and then you defective, defective. And then you can do probabilities based off of this. It's just basically another way of writing out your sample space, like what we did with the heads, 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 tails, tails, heads, tails, tails. There's another way of writing out your sample space. On a tree diagram, the number so on a tree diagram or for a sample space, your total number of possibilities is going to be the total number of outcomes here. Yeah, and then how many times you do it. So outcomes and then number of times as your exponent. Okay, so here I have 2 outcomes and I'm doing 2 pulls. So I get 4 total outcomes. So for example, if I roll a dice 3 times, or sorry, dice. Yeah, we'll do dice 2 times. There are 6 sides on a dice and you're rolling it twice. You're going to have 36 possible outcomes. A 1 and a 1, 1, 2, 1, 3, 1, 4, etc., all the way to 6 and then 6. Or if you do a coin 3 times, you have 2 outcomes, heads or tails, to the third. 2 to the third is 8. So you have 8 possibilities that you could get. You get head, 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 tails, heads, etc., etc. Okay. I think that is 4.3.